you very much. So I apologize that I cannot be there in person, and it's been challenging for me to follow workshops remotely. But thank you very much for organizing this and having me speak and present our work here. So I want to essentially give you an update on our experimental efforts on trying to develop a new platform with fermionic atoms that will allow us to study U1 quantum link models. And we have chosen to work with ytterbium atoms, having in mind that the SUN symmetric interactions of ytterbium will eventually pave the way towards studying more complex non-abelian quantum link models as well. So that's like the main plan that we have in mind. Just very briefly to set the stage. I'm working with cold atoms in optical lattices, which means that we have basically interfering laser beams where we trap the atoms on the minima of the lattice potential, which allows us very generally to study Bose and Fermi-Hubbard models in and out of equilibrium. So we typically have global control over the tunnel coupling J and the Hubbard interaction energy U. And what I'm trying to convince you is that maybe in order to find an efficient way to simulate quantum link models in our lattice models, it may be beneficial to actually add some local control to these tunnel couplings as well in order to engineer the desired local symmetries that we want. So basically what we aim for is to begin with any structure that looks like this, that looks like a lattice gauge theory, where what we need is in the end matter fields that hop between the vertices of the lattice and these link operators that live in between the two matter sites. And then we can try to engineer different types of symmetries. And we have particularly chosen to go for U1 and having in mind to make it more complex and study non-abelian. There has been a lot of progress during the recent years, and I'm going to give you a very brief summary of some of the experimental progress that happened in our community. But the main challenge that we face is really that we want to fulfill Gauss' law, so that we have this well-defined coupling between matter and gauge fields that fulfill the proper local symmetry. And this is something that does not naturally occur in our systems where we are typically dealing with global conserved quantities. Okay, so the progress that has been made has taken place on a number of different platforms. The one that is probably closest to what I'm going to tell you is the realization of U1 quantum link models in Bose-Hubbard chains, where the idea is that with additional local on-site potentials, you can engineer energy penalties that suppress single particle tunneling in a way that you end up with correlated tunneling processes that then respect the U1 symmetry. Now, this is one example that has been implemented in an extended 1D chain. There's a second platform that emerged, which seems very promising, which is Rydberg atom arrays, where indeed it has been shown that you can implement dimer models also in 2 dimensions. Now, they are, of course, a little bit different, and I'll get back to that. What we aim for is simulating matter and gauge fields in the same platform using fermionic atoms. So we really try to go to 2 dimensions, having fermionic statistics and having both available in the platform to study the gauge field degrees of freedom and the matter field degrees of freedom. And then the other 2 works that I briefly want to mention are spin-changing collisions. These have been implemented in a 2-site building block. And the idea is that you can make use of spin-changing collisions to implement the proper symmetries. And then there's a BC that lives on the link between the matter sites. And you can have fermionic atoms that hop around between the sites, which are here labeled with the index N. Now, this has been implemented with bosonic atoms so far, but there are schemes in order to extend this to 1 dimension as well. Now, all of this essentially happened in 2020. We have also worked on a different type of implementation, which made use of Floquet engineering, where the basic idea was inspired by previous works where we have used periodic driving and Floquet engineering in order to implement artificial gauge fields. So what we have done is, again, also in a building block of only 2 sites, to implement a C2 symmetry, a C2 lattice gauge theory coupled to matter, which is given by the Hamiltonian up here. So we have this hopping term A dagger A and a tau Z term that describes the link operator. And we have an additional energy for the C2 electric field, which is proportional to tau X. And the way we have implemented that was using two component bosonic atoms that we label as A and F. So one is implementing the matter and one is implementing the gauge field on the link. And by proper engineering of Fouquet-induced resonances of these tunneling processes, we managed to isolate the tau Z A dagger A term. And the link operator is then implemented in the imbalance of this gauge field particle between the left and the right side. So this works very well. We have analyzed this model and studied it experimentally. Now you can see that it's actually a little bit challenging to extend this to a fully coupled 1D chain because the link operator is implemented by this imbalance between left and right, which means that if you just naively now connect this to a 1D chain, there will in fact be some coupling. So one has to either work with 3 different internal states or have like an intermediate supersite, which is a proposal that we came up with. So this is basically the state of the art of what has been implemented so far. But none of these platforms are really well suited in order to go to 2 dimensions or have fermionic statistics in the platform. And this basically motivates the design of our new experiment, where we try to fulfill both of these criteria. Okay, so how do we do that? As I mentioned in the very beginning, we thought about finding an approach where we can combine the properties of the nice lattice potentials that we really work with and like, because they can be very large. We can generate large systems and they are basically defect-free, but they do lack local control. So we thought, okay, maybe it's a good idea to combine these lattices with local control by adding an array of tightly focused laser beams, also known as optical tweezers. And then in order to fulfill the proper local symmetries, of course, we have to find the proper Hubbard model that we can then map onto a lattice gauge theory. And for that, we have designed a mapping that I'll explain in a second. But what we need for that is a local state-dependent control of the tunnel coupling. So essentially what you see here in this black line is a superlattice potential where every other side is lifted by an energy penalty delta. So there would be no tunneling whatsoever. But now the idea is that if you add a tightly focused laser beam on this high energy side, you can lower the energy penalty and make it resonant. So this is one of the key ingredients that we need in order to simulate the U1 lattice gauge theory. So basically we have shifted the complexity of implementing the model towards an engineering task of the proper optical lattice. But then if we manage to do that, we can actually work with a single species. So we can work with ytterbium atoms and just make use of the 2 available clock states, the ground and metastable excited clock state of ytterbium, which essentially we treat as 2 different species. And this then simplifies the complexity of the machine because we don't have to work with mixtures. And this may sound a little bit crazy if you think about controlling the tunneling locally in such a lattice, and it is indeed very challenging. But I think the recent progress that we have seen, for instance, in Adam Kaufman's lab at Chile, is very promising. They have managed to actually load atoms from a tweezer array into a normal standing wave optical lattice and see coherent quantum walk dynamics. So this is still not as challenging as controlling locally a tunnel coupling, but I think we are on a very good track. So this makes us quite confident that we will get this to work. And also another work that goes along similar lines, which has been implemented with lithium atoms from Wasim Bakar's group, is having actually a tweezer array with arbitrary shapes where lithium atoms can tunnel between neighboring tweezers. So this is also similarly challenging because any potential corrugation between neighboring tweezers would dephase your tunnel oscillations. So all this goes in the correct direction, and we'll try to combine this now in order to simulate lattice gauge theories with ytterbium atoms. So let me say in a little bit more detail how the schematic or the mapping works. So here what you see is actually two decoupled chains, which are labeled as G and E. So that's the clock state atoms. We have the ground state G and the metastable excited state E. Now what we want to do is engineer a triple well lattice. So these double lines mean that there's hopping between these neighboring sites, resonant hopping. And the dashed line means that there's an energy penalty. So atoms can actually not hop onto the site, which is connected with a dashed line. So we want to engineer this type of lattice and a similar one for the excited state, but shifted by two lattice constants. So these are the bright blue points. Again, the two solid lines label links that are connected by a tunnel coupling T. And if there's no interaction between the two states, then these chains are basically decoupled. But we will make use of a strong on-site interaction UEG, which then allows us to isolate correlated tunneling processes of fermions, of two fermions, which is then the basic dynamics of the model. Now you can see that in this specific lattice configuration, there are two different types of sites. The one that I marked with a red circle is a site where in principle both states can tunnel onto. And we will map this onto a link site or gauge field site, while the site next to it, which can only be either occupied by a ground state, or this one, which can only be occupied by an excited state, will be mapped onto a meta site. And in the end, because here we only consider two different states, this maps to a spin 1/2 quantum link model. And the process that we are going to isolate by adding additional energy penalties to suppress single particle hopping is of the form shown on the lower right corner. So we isolate a correlated tunneling process, which looks as follows. So let me first go up here again on the triple well schematic. Now let's just assume that initially, I hope you see my mouse, that this site over here is occupied by a ground state atom. And the neighboring site is occupied by an excited state atom. And all single particle tunneling processes are blocked by an energy penalty little delta. So then this ground state atom cannot hop onto the link site because it would have to pay a large Hubbard interaction energy. But what can happen is a correlated hopping process where the ground state atom hops to the neighboring site and at the same time an excited state atom hops also to the neighboring site. So this is also shown schematically down here, where the starting point is shown as these lightened up balls, while the final state is connected by the correlated hopping process is shown with this light blue and dark blue points. So that's a correlated hopping process, which then has the strength T square over U because it's a second order hopping process. And now you can interpret this hopping process as a hopping of the matter from one side to the other, and while changing the internal state of the link field, of the gauge field on the link. And the mapping then looks of the form that you have an A dagger A hopping and a spin raising S plus operator on the intermediate site. So that's the basic idea of the whole scheme that we are trying to implement. And for this, of course, we first need to be able to engineer this triple well lattice in the state-dependent way that is drawn on top of the slide. And how do we do that? So first of all, we implement with the dark solid line a magic optical potential that has the same shape for both states, G and E. And it has this energy penalty delta between neighboring sites so that there's no hopping. And now comes the idea of this local addressing. So now we shine in an additional focused laser beam in order to lower this barrier and induce resonant tunneling. It's purely static. So we really just focus a static potential onto this intermediate site. And this will give us this triple well configuration where indeed the next site over here is still penalized by an energy offset delta. And now the key thing is that we can do that in a state-dependent way. So we can shine in this local potential using a wavelength such that the potential is only seen either by the ground state atom or by the excited state atom. Now, by doubling this setup for the local tweezer beams, we can generate exactly the type of potential that we need for the ground and excited state atoms. And then that looks like this. So we have the dark blue and the light blue focused tweezer array, which then makes respectively the triple well lattice for the ground or excited state atom. And so that I mentioned briefly, so this is the quantum link model that we are engineering. It has this link operator x plus 1, which is in our case a spin raising S plus operator. And just to give you a simple example of what the type of dynamics could look like that we can study in the system, here you see the mapping towards electrons and positrons. How do we interpret the occupation on the different sites? So the matter sites, which have an odd number, an empty site corresponds to vacuum, while an occupied site corresponds to an electron. While for the even matter site, it's the opposite. So an empty site actually corresponds to an atom sitting there, and having no atom there corresponds to a positron. So if we start in this model with an initially empty vacuum lattice, we need to fulfill the following occupation. So just now focus on the first line. So here you see that we have placed the ground state atoms on the link sites. So this initializes the electric field in a certain initial configuration, for instance, +1/2 on every link. And then for the matter sites, you see that the occupation was chosen in a way that it corresponds to vacuum, an empty chain. Now, if we turn on the dynamics, which are these correlated hopping processes, which means that now actually this excited state atom can only hop over if the ground state atom hops over as well. Then you see in this mapping that we have actually generated an electron-positron pair. So in this simple implementation, we would be able to see pair creation processes of electrons and positrons. So this would be one of the first things that we would try to see in these types of experiments. Now, the key design choice for this type of lattice, so you may wonder if there is no easier way in order to realize these type of triple well lattices, was to find a scheme that can be extended to 2D. And indeed, we have shown that this idea of addressing the sites can be straightforwardly extended to 2 dimensions as well. And we have started to do ab initio calculations of the band structure because actually writing down the tight binding models and isolating the proper correlated hopping processes is very easy on paper, but if you look at the full potential that is generated optically, there are many other processes to worry about, and there are a lot of energy scales to consider at different hierarchies. And so we have set up this collaboration with Marcello, Francesca, and Pierre in order to figure out that indeed this implementation works, and with very promising results, which hopefully will appear in the archive very soon. So let me give you an update on the experimental progress that we have made in the meantime. So this is the energy level structure of ytterbium atoms that we want to work with. And here with the yellow arrow, I indicate the ultra narrow clock transition between the ground state 1s0 and the excited state 3p0. That's the 2 states that we want to work with. And in order to be able to do that, of course, we need to be able to address this transition to begin with. And the different state-dependent potentials that we need are again summarized here as follows. So just to fix the terminology, when I say that we implement a magic lattice, it means that the AC polarizability for the ground and excited state are exactly the same. And if we speak about tune-out wavelengths, G or E tune-out wavelengths, it means that only one of the 2 states sees any potential at all. All right, so then we can use the tweezer arrays at the tune-out wavelength to do exactly what I just described on the previous slide. All right, so now you go ahead and calculate the AC polarizabilities for the 2 states, and you will figure out that actually for ytterbium, the error bars on these calculations are fairly large. So the first thing that we did was actually to build a spectroscopy experiment in order to figure out where the special points in the AC polarizability curves are. So these crosses actually mark the locations of magic wavelengths. And this dot here marks the position of the G tune-out wavelength. And what we also want to know is the E tune-out, but this one, unfortunately, we could not measure yet. So what we have measured are these 3 points, which will also decrease the error bar on the prediction of the E tune-out wavelength. Now, the building of the experiment happened over here. So this magic wavelength is the typical clock magic wavelength at 759 nanometers, where the optical clock experiments work. And that's also what we have decided to start with. So that's our experimental setup. That's the vacuum system. We are working with a commercial ytterbium atom source from AOSense, which has an integrated Siemens slower. We have a 2D mod in order to collimate the beam. Then the atoms travel along this narrow tube and end up in this glass cell over here. Here we have additional slowing beams to reduce the velocity of the atoms below the capture velocity of our green 3D mod. And then we directly load it on the narrow line 3D mod at 556 nanometer, which is the 3p1 transition. And now for the first spectroscopy measurements, what we did was to build, these are the red arrows over here, a 1D magic optical lattice at 759 nanometers and do clock spectroscopy. And here's a picture of our first bosonic ytterbium mod. And here's a schematic of the setup that I just described. So that's the final glass cell. The green beams show the mod, and the yellow line shows the optical clock. And these little stripes here are the magic lattice at 759 nanometers. So we have chosen to go to very deep lattices, such that we can actually directly load the atoms from the mod into the 1D lattice without any need for further cooling. And then we end up with about 10 to the 5 atoms at 15 micro-K. And here you see this beautiful spectroscopy data, which I'm very happy to show you. We are very excited that this works. So this is driving transitions between the ground and excited state atom on the clock transition. And this Fourier limited line width that you see here is on the order of 30 Hertz. So we can actually go down even a little bit more narrow. And we have also seen first promising results of sideband cooling on the clock transition that we can apply as well. Okay, so that's actually an ideal starting point to figure out where the other special points in the AC polarizability diagram are. Because now you can imagine figuring out where the magic wavelength at the lower range is by just shining in an additional beam and measuring the differential light shift on your clock. And this is what is labeled here as this green beam, the OPO beam. So that's a laser that we borrowed from Hübner. And here you see an example of how the spectroscopy data looks like. In gray, you see the clock spectroscopy without the additional beam, the additional dipole beam. And in blue, you see the one where we have the dipole beam on. And now the resonance of the clock is, of course, shifted. And we can extract this differential shift as a function of the power of this additional dipole beam, but also as a function of the wavelength of this additional dipole beam. And here you see one such exemplary curve where we measure the resonance shift as a function of the power in the beam. And this allows us to then extract the magic wavelength, which occurs exactly at the location where this differential shift vanishes. And this type of measurements we have used to identify 2 additional magic wavelengths, which are here labeled as these red circles. The tune-out wavelength measurement works slightly different, but it follows a similar idea. So now the tune-out wavelength, remember, is the one where, in this case, the ground state atom does not see any potential. So in order to measure that, we retro-reflect this additional dipole beam in order to generate a lattice. So this is shown here in green, which is overlaid or superimposed onto our magic wavelength shown in red. So the green one is the tune-out one that we want to measure. And now we periodically modulate the amplitude of this tune-out lattice on resonance, which corresponds to a transition, a parametric heating resonance in the red lattice. So if you modulate this on resonance, typically the atoms are heated very quickly out of the trap. But of course, this scales with the amplitude, modulation amplitude of this additional heating lattice. So if we change the wavelength of this additional heating lattice and hit the tune-out point, then the heating should go away. And that's exactly what we did. So here you see 2 exemplary curves, how the atom number drops as a function of modulation time in a reference measurement where the modulation is off, shown in dark gray, and when the modulation is on, shown in dark blue. And from the change of this relaxation rate, we can deduce the heating rate that we impose by modulating this additional tune-out lattice. And now if we scan and measure this additional loss rate as a function of the tuning or as a function of the wavelength of this additional green lattice, we find a special point where this additional loss rate essentially drops to 0. And this is exactly where the tune-out wavelength scales. So this loss rate goes as the detuning from the tune-out squared. Okay, and with this, we have basically identified most of the important wavelengths that we need in order to build our lattice potential. Now, the next step is actually to arrange the atoms in a two-dimensional lattice. And for that, we need 2 additional ingredients. So first of all, we need to be able to load the atoms from the mod directly in a two-dimensional lattice. This is can be done similar to what I've shown you with the 1D lattice. But then we want to cool them to the ground state in order to be able to do coherent Hubbard dynamics. And because we decided to directly load the atoms from the mod into the lattice, we will end up with a stochastic filling. So we need a tweezer array in order to rearrange the atoms in the desired initial state configuration. And so we have set up a tweezer array, as you see in here. So that's an optical image of our tweezer array from our test setup. And we just started now rebuilding our machine in order to integrate that into our experimental setup. And in the meantime, so you saw that I've shown you the picture from a bosonic mod. In the meantime, we have also switched to fermions already. And yeah, with this, I would like to conclude. So basically, we have designed this new platform to simulate U1 lattice gauge theories, which also works in 2D. So that's the schematic shown on the right. And we continue thinking about how to use the different internal states of fermionic ytterbium atoms with SUN symmetric interactions in order to extend this to non-abelian quantum link models. And just to mention, in case people are interested, this U1 quantum link model that has been implemented in 1D bosonic chains, we have now also realized in our cesium quantum burst microscope. So we are also thinking about additional experiments that we could do along these lines with bosonic atoms even. And with this, I would like to thank the ytterbium team who has done a fantastic job in building the machine. And I hope that very soon we will be able to share results of fermions in a 2D lattice. So thank you very much.